Salts can form acidic solutions, neutral solutions, or basic solutions when dissolved in water. For example, if we dissolve sodium chloride in water, solid sodium chloride turns into sodium cations and chloride anions in solution. At 25 degrees Celsius, the aqueous solution of sodium chloride is neutral and has a pH of 7. The reason why the pH is equal to 7 is because neither the cation nor the anion reacts with water, and water has a pH of 7 at 25 degrees Celsius. And since neither the cation nor the anion react with water, the pH remains 7. In a different solution, it's possible for the cation or the anion to react with water and turn the solution either acidic or basic. Therefore, to predict if a salt solution is going to be acidic, neutral, or basic, we have to analyze whether or not the cation and the anion will react with water. And there are 4 possible combinations of cation and anion. The first combination is neither the cation nor the anion will react with water. And if that's the case, the resulting solution will be neutral. We've already talked about an aqueous solution of sodium chloride being a neutral solution. The way to approach this is to look at the chemical formula and say sodium chloride consists of a sodium cation and a chloride anion. The next step is to analyze the cation and the anion and think about if they react with water or not. To determine whether or not a cation will react with water, it's helpful to think about a list of common strong bases that consist of group 1A metal hydroxides and the heavier group 2A metal hydroxides. If the cation is from group 1A or the heavier group 2A, the cation will not react with water. For example, in our case, we have the sodium cation, and since the sodium cation is in group 1A, the sodium cation will not react with water. Next, we think about the anion. To determine whether or not the anion will react with water, it's helpful to think about a list of common strong acids. If the anion is the conjugate base to one of the strong acids, the anion will not react with water. For example, in our case, we have the chloride anion, which is the conjugate base to HCl. Since Cl- is the conjugate base to HCl, Cl- will not react with water. A good way to think about this is to think about hydrochloric acid being a strong acid, and the stronger the acid, the weaker the conjugate base. Therefore, the chloride anion is such a weak base, it will not react with water. So we say the chloride anion is of negligible basicity. And since neither the cation nor the anion react with water, an aqueous solution of sodium chloride will be neutral. As another example, let's think about barium nitrate. Barium nitrate consists of the barium 2+ cation and the nitrate anion. Because the barium 2+ cation is from the heavier group 2A, the barium 2+ cation will not react with water. And because the nitrate anion is the conjugate base to a strong acid, which is nitric acid, the nitrate anion will not react with water. Since neither the cation nor the anion will react with water, an aqueous solution of barium nitrate will be neutral. The second possible combination of cation and anion is where the cation does not react with water, but the anion does. When this combination occurs, the resulting solution will be basic. An example of this second combination would be barium acetate. So barium acetate consists of the barium 2+ cation and the acetate anion. Since barium 2+ is on our list for heavier group 2A, barium 2+ will not react with water. However, the acetate anion is the conjugate base to acetic acid, and acetic acid is a weak acid and is not on our list of strong acids. Since acetic acid is a weak acid, its conjugate base is strong enough to react with water. So the acetate anion is a strong enough base to react with water, and when acetate anion reacts with water, it forms acetic acid and hydroxide ions. Since the concentration of hydroxide ions in solution have increased, that's what makes the solution basic. This is called anion hydrolysis, when an anion reacts with water to increase the concentration of hydroxide ions in solution. As another example, let's think about sodium hypochlorite, which consists of the sodium cation and the hypochlorite anion. Since the sodium cation is from group 1A, the sodium cation will not react with water. The hypochlorite anion is the conjugate base to hypochlorous acid. Since hypochlorous acid is not on our list of common strong acids, it must be a weak acid, and if it's a weak acid, its conjugate base, the hypochlorite anion, is a strong enough base to react with water, therefore increasing the concentration of hydroxide ions in solution. So since we have a cation that does not react with water and an anion that does react with water, an aqueous solution of sodium hypochlorite will be basic. The third possible combination of cation and anion is where the cation will react with water, but the anion will not. In this case, the resulting solution will be acidic. As an example of this third combination, let's consider an aqueous solution of ammonium nitrate. Looking at the chemical formula for ammonium nitrate, it consists of the ammonium cation, NH4+, and the nitrate anion, NO3-. First, let's talk about the anion. The nitrate anion is the conjugate base to nitric acid, which is HNO3. Since nitric acid is a strong acid, its conjugate base is of negligible basicity, so the nitrate anion does not affect the pH of the solution. It does not react with water. When thinking about the cation, NH4+, NH4+ is the conjugate acid to NH3, which is ammonia. And since NH3, or ammonia, is a weak base, its conjugate acid, NH4+, is strong enough to react with water. And when the ammonium cation, NH4+, reacts with water, it forms the hydronium ion H3O+ and ammonia. So the NH4+ is increasing the concentration of hydronium ion in solution, which is what's making this solution, this aqueous solution of ammonium nitrate, acidic. As another example, let's consider aluminum chloride, an aqueous solution of aluminum chloride. Looking at the chemical formula, aluminum chloride consists of the aluminum 3+ cation and the chloride anion. The chloride anion is the conjugate base to hydrochloric acid, which is a strong acid. Therefore, the chloride anion does not react with water. The aluminum 3+ cation is not from group 1A or a heavier group 2A. Therefore, we can conclude that this is going to react with water. So small cations with charges of 2+ or greater can react with water. Let's look in more detail how the aluminum 3+ cation can function as an acid. In aqueous solution, the aluminum 3+ cation interacts with water molecules to form a hydrated metal ion. Water is a polar molecule, and the positively charged aluminum 3+ cation interacts with the negative end of the water molecule. So there's an electrostatic attraction between the negative end of the water molecule and the 3+ charge on the aluminum cation. I only drew in one water molecule. However, keep in mind there's actually 6 water molecules interacting with one Al3+ cation in the hydrated metal ion. The strong electrostatic attraction withdraws electron density from this oxygen-hydrogen bond, which makes this proton easier to remove. Therefore, when another water molecule comes along, so right here in the equation, this other water molecule can take this proton, leaving these electrons behind on the oxygen, and if you're adding an H+ onto H2O, you form H3O+. Losing an H+ means the charge in the hydrated ion went from a 3+ down to only a 2+. And increasing the concentration of hydronium ions in solution means the pH of the solution will decrease. Therefore, a hydrated metal ion can function as an acid. However, it's the strength of this interaction between the cation and the water molecules that determines if the hydrated metal ion will function as an acid or not. For a small cation with charge of 2+ or greater, that gives a large electrostatic attraction to the water molecule, which makes this proton easier to donate. However, if the cation is too large or the charge is too small, the electrostatic attraction is not strong enough to make the proton easy to donate. And that's the reason why cations from group 1A or the heavier group 2A don't interact strongly enough with water to affect the pH of the solution. Therefore, if we have an aqueous solution of aluminum chloride, the cation, aluminum 3+, will react with water, but the anion, the chloride anion, will not. Since the cation reacts with water, the resulting solution will be acidic. The fourth possible combination is where a cation will react with water, and the anion will also react with water. In this case, the resulting solution can be acidic, neutral, or basic. As an example, let's think about an aqueous solution of ammonium carbonate. Looking at the chemical formula for ammonium carbonate, the cation would be the ammonium cation, so that's NH4+, and the anion would be the carbonate anion, CO3 2-. We've already seen that the ammonium cation will react with water, and the carbonate anion, if you add a proton onto it, that doesn't give us an acid on our list of strong acids. Therefore, the carbonate anion is a strong enough base to react with water. First, let's look at the equation showing the ammonium ion reacting with water. So this is cation hydrolysis, since the cation is reacting with water. In this case, we would form the hydronium ion and ammonia. Next, we think about the carbonate anion reacting with water. So this is anion hydrolysis. When the carbonate anion reacts with water, it forms hydroxide ions in solution and also hydrogen carbonate. Since the cation hydrolysis forms hydronium ions, if we were to write an equilibrium constant for this acid-base reaction, it would be Ka. And since the anion hydrolysis forms hydroxide ions in solution, if we were to write an equilibrium constant for this acid-base reaction, it would be Kb. To figure out if the aqueous solution of ammonium carbonate is acidic, neutral, or basic, we need to compare the Ka value for ammonium to the Kb value for carbonate. If the Ka value is greater than the Kb value, the solution is acidic. If the Ka and the Kb values are approximately the same, the solution is about neutral. And if Ka is less than Kb, or you could say Kb is greater than Ka, the solution will be basic. To find the Ka for the ammonium cation, we're going to use the following equation. Ka times Kb is equal to Kw. And this equation is true for a conjugate acid-base pair. So what this is saying is the Ka for the ammonium cation times the Kb for ammonia is equal to Kw, which at 25 degrees Celsius is equal to 1.0 times 10 to the negative 14th. Textbooks often have the Kb values for common weak bases like ammonia, and the Kb value for ammonia is 1.8 times 10 to the negative 5th. So we solve for Ka, and we find that Ka for the ammonium cation is equal to 5.6 times 10 to the negative 10th. To calculate the Kb value for the carbonate anion, we use the same equation. Ka times Kb is equal to Kw. However, remember, this is the Ka and the Kb for a conjugate acid-base pair. So we're talking about the carbonate anion as the base and its conjugate acid, which would be hydrogen carbonate HCO3-. So we plug in the Ka value for HCO3- and solve for Kb. So Kb for the carbonate anion is equal to 1.8 times 10 to the negative 4th at 25 degrees Celsius. And this Ka value is also at 25 degrees Celsius. Looking at the values for Ka and Kb, Ka is less than Kb. Since Ka is less than Kb, or we could say Kb is greater than Ka, this solution is basic.